Welcome to my channel. In this video, I'm going to show you how to implement a Butterworth Lowpass filters based on open circuit stops only. So to begin with, we need to determine the order of the filter. And suppose you have a filter characteristic that can be summarized by this graph. You have the passband gain AP here. AP should be 3 dB below the midband gain. So you should have 3 dB here. The so-called passband frequency should be this one here. The stop band is somewhere here. The stop band is always associated with the stop band attenuation. And to determine the order, you need to use this formula. And this is a very common formula. And the next step that you need to do is to determine the filter coefficients. For Butterworth filter, the coefficients can be either extract from the prototype tables or equally you can use the formula. The formula is very simple. For Butterworth filter, the formula is this. K here is equal to 1, 2 until n. And the first step is to apply Richardson transformation. And this step is pretty straightforward. The purpose of this step is to convert all the discrete or lump elements into open and short circuit stop. Step 4 is a little bit tricky. The next step, because we normally implement the filter on a printed circuit with no short circuit stops. And the way how we do it is to use colloidal identity. Colloidal identity. And perhaps before giving any examples, I'm going to explain how we can use the Kuroda identities uh, more efficiently. So step 4, Kuroda identity. The purpose of this step is to replace all the short circuit stop with open circuit stops only. So before doing anything, I think it's important for me to explain how we can use these identities more efficiently. According to my experience, uh, the lump element model is not easy to use. Uh, for example, for identity number ones, uh, I think it's better to replace all the lump element with transmission line. And we don't use any n square. And by doing this, we will end up with the characteristic impedance for these transmission line sections uh, with this value. And together with a short circuit stop, the characteristic impedance of this short circuit stop is so this is Kuroda identity number 1. And we have another Kuroda identity which is also frequently used. And this is the one that begins with short circuit stop. And this one is the one that we need for our filter implementation. And all the lengths here should be lambda g divided by 2. And if you do it carefully, you will end up with the length here, lambda g divided by 2 by a, and we will end up with an open circuit stop. And this is how we replace all the short circuit stop with open circuit stop. So I hope this is the easiest way. And now I'm going to show you an examples. Example, So suppose we are going to design a Butterworth filter, low pass filter. According to the following specifications. The pass band frequency is 3 GHz. The stop band frequency is 3.5 GHz. The stop band attenuation is 15 dB. So as I said in the beginning, the very first thing that you need to do is to determine the required order of the filter. So step one, we are going to determine the order of the filter. Using the formula here, and if you substitute the value from the question, you will get the stop band 15 and divided by 10. The pass band is 3, yeah, 3 dB, 3 gigahertz, and sorry, 3.5 gigahertz and 3 gigahertz. So if you do it carefully, you will end up with an answer 2.42. But the order should be an integer value. What you are looking for is the integer, the next integer larger than 2.42. So the next integer larger than 2.42 is 3. The required order of the filter is 3. Now the next step is to determine the filter coefficients. So step 2. The filter coefficient can be calculated using this formula. And g of 1 will be equals to sine 2, 1 minus 1 to n pi. And this will end you up with an answer 1. G2 will be 2 sine 2 times 2 minus 1 to n and then pi, and this will end you up with 2. And G3 will be 2 times sine and then n is 3, yeah? And this will end you up with 1. And G4, you need to add one more stage, which is G4. And this is also the final stage. The coefficient for this stage is always equals to 1. And with this in mind, you can immediately come up with a schematic circuit for the filter. The schematic circuit will be like this. And the first stage 1, is 1. And this is G1, yeah? The value is 1. And the inductor G3, G2. So this is the filter. assuming that the low impedance is 1. But obviously, you don't want this filter because in microwave frequency, you will not be able to come up with a correct discrete value. So what should we do? We are going to replace all these lump elements into distributed elements, the so-called open circuit stop and short circuit stop. So what should we do? What we can do is we replace all the inductor with open circuit stop. The characteristic impedance is for G1, the characteristic impedance is G1. For G3, the characteristic impedance is G3. The length of each of the stops is lambda G divided by A. For the capacitance, we will have an open circuit stop. And the characteristic impedance is 1 over G2. And the length here is obviously lambda G divided by A. So this is the circuit that we need. This is so-called Richards transformation. Now the next step is to make sure all the short circuit stops are replaced with open circuit stop. The reason why we don't want short circuit stops is it's difficult to implement in printed circuit. It's also difficult to implement in integrated circuit. So to begin with, we need to make sure we are going to add two more blocks. One for the output. The characteristic impedance here is equal to 1. The length here is lambda G divided by 2. By doing this, you are not going to affect the circuit performance. And similarly, we are going to do the same for the input port. The length here is also lambda G divided by A. And this is the circuit that we are going to use for the next step. So next step is to replace all the short circuit step with open circuit step using the technique so-called Kuroda identities. The identities that we need is identity number 2. So step 4, Kuroda identities. We don't need to use all the Kuroda identities. We only need to use the right one. I remember Kuroda identity number 2 is like this. ZL 1 plus Z0 divided by ZL. So this is a lot easier. Z0 and we call what we have done from the last step. From last step, we had a circuit. The circuit is like this. G1, G3, one, one, so this is the circuit from the last step, 1 over G2. And if you look carefully, you will notice that this section, the combination of G3 together with the newly added transmission line section, is very similar to this one, the identity 2. And what we are going to do is to take advantage of the corona identities and convert this one into this one. So this one will be equals to DL, which is G3. So G3. And then 1 plus V0 is 1, VV is G3. And we will eventually end up with a parallel open circuit stop, and V0 here is 1, and 1 plus 1, and then G3. So this is the idea. And if we do it carefully, you will notice that after transformation, we got this, and for the capacitance, for the open circuit stop in the middle of the circuit, we don't need to do anything. But for the combination of G1 and the transmission line section at the inputs, this is exactly the same as the one at the output, with the only exception that you have the left and right mirroring. So in theory, this one here can be replaced with this one. Well, of course, the left and right has to be attached. So if I do it carefully, step 4. Should be like this. This step will be equal to G1 1 plus 1 G1, and we will have a open circuit stop and 1 plus 1 over G1. So now we have almost symmetrical now. We just need to rewrite this circuit. Yeah, rewrite this circuit. So we draw this circuit. So let me organize a little bit here. So what we need to do now is to continue with step 4, and we draw the circuit more clearly. So after the conversion, we have G1, 1 plus 1 over G1. And I'm going to calculate all this value on the fly. G1 is 1. 1 plus 1 over 1, which is 2. And we have 1 times 1 plus 1 over 1, which is 2. And this one here is 1 over G2, which is 1 over 2. And this will become 0.5. And this one here will be exactly the same as the one here. And this will become 2. And this one here will be like this. And 1 plus 1 over G3. And this is 1, 1 over 1. And this is 2. So it's symmetrical. Left and right symmetrical. And do not forget that there will be impedance at the output, and we also have impedance in the input. So this is so-called step 4. Basically, the circuit is done, but we still need to do some more steps. First, we need to determine we need to scale up all the impedances by 50, because the circuit is based on 50 ohm, not 1 ohm. So this is the next step. So step 5 is the step for scaling. So let's do it carefully. And this one will become 50 ohm. This one here will become 2 times 50. So 100. And this one is 2. So this transmission line section here is 2 times 50, which is 100. And this one here is 0.5 times 50 here, which is 25. And this one here will be the exact same copy of this one, 100. And this one here will be 2 times 50, 100. And the low impedance here is 100. And do not forget that the length should be lambda divided by A. And lambda, we need to do some calculation. V A V so it should be 33 millimeter. 33 millimeter. The length here should be 33 millimeter. The length here is 33 millimeter. And the length here is 33 millimeter. And the length here is also 33 millimeter. So the filter design is done. There's nothing difficult at all. And more importantly, I don't need to struggle too much when we when we did the colloidal identities. If you have any questions and you want to ask me, you can either come to my office or leave your question to the comment sections in the below the video. Thank you.